So we have a great exam. Differential Equations Exam 2. We're talking systems. We're talking matrices. Woohoo! Lots of stuff for us to look forward to. We've got 6 problems to do. This particular exam was from fall 2025, a good vintage. And so we'll get ready. Of course, as always, we begin by putting our name on the test because we're going to do some good works and we want to get some good credit. All right, let's begin. Number 1, use the substitution method or de-operator method to find the general solution for the following system of equations. So we actually have a choice. We have sort of a choose your own adventure here. We have substitution or de-operator. Now, I would say because we're trying to find the general solution, I think substitution I might lean towards that, just because if I do the de-operator method, the thing is that you get a nice way of doing that. By the way, de-operator we sometimes call it Cramer's rule method. And the issue is, well, yeah, it gives you a nice differential equation for x, and you get a nice differential equation for y, but how do you tie the two together? And that tying together can be non-trivial. Whereas substitution method, it's pretty easy to tie them together. All right, so what do? What we're looking for is in substitution, we want to put one inside the other. And so we look for our equations and we say, can we solve for one of our variables? Now you'll notice in the first equation, we have a single y. That's a good sign. And in the second equation, we have a single x. So we have one of two choices. We can solve for y in the first or solve for x in the second. Because of that 4, that would give me a fraction, and I always get nervous with fractions. So let's solve for y in the first. If we carry that out, we say, oh, well, y becomes x prime minus x. And now we're going to take that expression and plug it in to the 2 places where y shows up in the second equation. So that would give us our x prime minus x prime, y prime, is equal to 4x plus x prime minus x. Well, that becomes x double prime minus x prime, because it just means take the derivative of each piece. We'll bring these terms across. What do we have here? Well, we have a 4x and a minus x, so that's a 3x, bring it across. That's a minus 3x. And here, this comes across as a minus x prime. Or we have x double prime minus 2x prime minus 3x equals 0. And we're back to the kind of problem that we were doing on the last exam. All right, we've got something which has constant coefficients, linear, homogeneous. Put those together. Nice! We like nice differential equations because we have ways to solve it. We can take that differential equation and turn it into an algebra problem. So in particular, we say, well, there's a characteristic polynomial, and replace our derivatives with power. So like r squared, second derivative, minus 2r, first derivative, minus 3. No derivatives, no term. And now we say, well, try to factor. And our teachers are nice to us, so they give us something that could factor. We always have the quadratic formula in our back pocket, so we need it. Quickly double check. R squared, good. Plus r minus 3r is minus 2r. Minus 3 times 1 is negative 3. Which means that we have roots of 3 and negative 1. Now, each root becomes a solution. And so this root of 3 says, okay, we have e to the 3t. And this root of minus 1 says, okay, we have e to the minus 1t, which we write as e to the minus t. Now, those are individual solutions. Because we have something linear, we can do superposition. And so our general solution for x, because we were solving for x, is some linear combination. Okay, so here's our x. How do we get y? Well, that's where this formula comes in. So we say, okay, y is x prime minus x. And so, well, we know what x looks like. So we say x prime would be taking the derivative 3a e to the 3t minus b e to the minus t. Then we minus x, which would be a e to the 3t plus b e to the minus t. And if we do that, we get 3a minus a, 2a, oh yeah, you betcha, 2a, minus b e to the minus t, minus the b e to the minus t, which would make it a minus 2b e to the minus t. And again, there's our y. And now we're done. But to help the grader quickly spot our problem's answer, right? We want to make life good for the grader. Happy grader, more points. Well, more realistically, it is to say, if we have organized work, the grader can easily spot where to give us partial credit. If our work is disorganized, well, they can't spot where to give us partial credit, and so we miss out. So put in the time to have your work be nice and organized, and let the grader know where your answer is. So there we go. There we go. All right, that's number 1. Moving on to number 2. Consider the differential equation x triple prime. That's right, 3 derivatives equals 2x prime minus x, where x prime denotes dx dt and so on. So there's an unknown variable and we're calling it t. So there's 2 parts. Part A, convert to a system of 3 first-order linear equations. And part B says, put that into a matrix. Into the matrix. Okay, so what's the idea? You have sort of this, I don't know what the right analogy is, sort of, I'll say a seesaw, which is you say, I have the number of equations involved and the order of the derivatives involved. So you could say, well, I could have a very high order but few equations, which is what we currently have, or a very low order of derivatives but many equations, which is what we're trying to get. And which one's right? Well, they both have good uses. So I'm not saying one is right and one is wrong. But how do we go about solving this? Well, if we want to get it down to a large collection of first-order linear equations, that says we can only involve first derivatives. So how do we get to a third derivative? Well, we're going to sort of climb a ladder. So here's our idea. Third derivative, we're going to introduce 3 functions. And the first function we'll introduce, so we're in part A, we're going to call that the function we're interested in. x1 is x. Climb the ladder. x2 is x prime. x3 is x double prime. Now you'll notice when we said x2 is x prime, well, that's the same thing as x1 prime. x3 is x double prime. Well, that's the derivative of the first derivative. That's x2 prime. So we climb up. We don't need to get to x triple prime. We're going to do that in a slightly different way. So we've introduced some variables. Now we say, all right, we want to write it as the first order linear equations. So the idea here is we're going to have our derivative of our xi, and then we're going to have equals stuff without derivatives. And we're going to do that for each one of our 3 variables. So we say, okay, we have an x1 prime, an x2 prime, and an x3 prime. Well, what is x1 prime? Well, we have an x1 prime. It is x2. So oh, nice. So x1 prime is x2. x2 prime is x3. Cool, cool, cool. What about x3 prime? Now, what do we have? Well, notice, what can we say about x3 prime? That's x triple prime. And we notice that x triple prime, this is where our original differential equation comes in. So the original differential equation comes in at essentially this entry here. Well, that is 2x prime minus x. But where is x prime? Well, x prime is x2. So this is 2x2, and x is x1. So we get 2x2 minus x1. And that is part A. Cool, 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 cool. Now, part B says, hey, here is this system, put it into a matrix form. Well, how do we do that? Here's what I do when I'm thinking about putting it into a matrix form. And what I'll do is I have my system, and I'm going to rewrite it in a very particular way. So I have the x1 prime, the x2 prime, and the x3 prime. And what I'm going to do, and I'll put a little color here, is I'm going to say put the x1 terms here, the x2 terms there, and the x3 terms there. All right? So what do we have? Well, x1 prime just has a single x2 term. x2 prime has an x3 term. And x3 prime, well, there's a minus x1 plus a 2x2. Now, just to really lean into this, you might say, gosh, there's a lot of white space. Well, that white space, the way you should think about it is there's a 0x1 plus, I'll think of it as a 1x2 plus a 0x3. Here there's a 0x1 plus a 0x2 plus a 1x3. Then there's this minus 1x1 plus 2x2 plus 0x3. And what's going on is, what does a matrix represent in terms of a linear system? It's storing coefficients. So I'm writing it in this way so that I can get the following. So I'm going to now put everything into the matrix. So I have the x1, x2, x3 prime, right? That's there, is equal to this 3 by 3 matrix times x1, x2, x3. And now I just read off the coefficients. 0, 1, 0. 0, 0, 1. Minus 1, 2, 0. And that's it. That's putting it into matrix form. And so we're done. Yeah, it's really the key thing is to understand, oh yeah, that matrix is storing coefficients of these equations. And so if I just rewrite the equations in a nice way, in particular like setting them up almost like it were in a square grid, line up all the variables together, then I can just read off where things go. All right, that's number 2. Which brings us to number 3. Consider the non-homogeneous system. X prime is 1, 2, 0, minus 1, x plus 1, 2. So this plus 1, 2, this is our non-homogeneous part. All right, cool. So non-homogeneous part. Now what do we need to do? Well, we're given that x is c1 e to t1 0 plus c2 e to the minus t1 minus 1 is the general solution for the associated homogeneous system. So in particular, this x, we would call it xc, the complementary solution. And that comes from where? It's like cover up that 1, 2. That's the corresponding homogeneous system. And we say, all right, find the solution for the non-homogeneous system with the initial condition x of 0 is 1, 1. Okay, so what's our challenge here? Or what's our game plan? What we need to do is we need to find the general form for solutions to the non-homogeneous system, and then we'll find out how to figure out to make the initial condition work. So, what do we have? Well, in general, we have x looks like xc plus xp. Now, xc is given to us, so we're not going to do any work to find that. Because xc is given to us, we're ready to tackle xp. And so for that, we're going to use undetermined coefficients. And say, all right, what's our plan for undetermined coefficients? Well, I like to say, let's make a list. Let's look at this function and say, what kind of little subfunctions, if you will, what are the pieces made of? And you might say, there's nothing. There's just numbers. Cool. So that's the function called 1. All right. Now, that's our list. That's what the function is made out of. Multiples of 1 and combinations of multiples of 1. We quickly check, hey, let's look at what solution showed up in xc. It's e to the t, e to the minus t, which doesn't overlap with our list at all. Nice. So we don't have to worry about it. So now we're like, okay, so what do we do? Well, we say, now that we have our list, and we say, well, our particular solution looks like something of the form 1, right? Take the function times a vector here, AB. And we're going to run it through this differential equation. So xp prime, what's the derivative of constants? The answer is 0. So here's our xp prime. That has to be equal to 1, 2, 0, minus 1, ab plus 1, 2. Right, here's our xp. Well, if we clean up here on this side, that's a plus 2b, right? A plus 2b plus 1, top entry. 0a minus b plus 2 in the bottom entry. And remember, this is 0, 0. Well, that leads us to, can move this up for a second, a system of equations. We get a plus 2b plus 1 equals 0, and minus b plus 2 equals 0. Well, the second equation is pretty straightforward. No big surprises. We like that. This tells us that b should be 2. Now that we know b is 2, we say, oh, 2 times 2 makes 4, plus 1 makes 5. So a plus 5 equals 0, which tells us that a has to be negative 5. All right, good, good. Now we know b and a. So we can come back up here and say our particular solution is negative 5 for a and 2 for b. All right, pull this back down. And, okay. We want to make sure I have xc available. So, we took care of our undetermined coefficients, which solved us, or gave us our xp. Now we have our general form. We just put it all together. So we have x is some constant c1, e to the t, 1, 0, plus some constant c2, e to the minus t, 1 minus 1, plus this negative 5, 2. Now, what's our next step? Next step, we need to solve for C1 and C2. Okay, so we're going to use our initial conditions to solve for C1 and C2. And so I'll just put a note here. Use initial condition to solve for C1, C2. And, well, plugging it in, we get that 1, 1. That's our x of 0. So we plug 0 into here. E to the 0 and e to the minus 0 are both 1. So that's going to make it a little bit easy to compute. That's C1, 1, 0, plus C2, 1 minus 1, plus negative 5, 2. Or, if we put that together, we get 1, 1 is C1 plus C2 minus 5. All right, C1, C2 minus 5. And 0, C1, 0, minus C2 plus 2. So we again get down to two equations, two unknowns. Wow, nice. That happens a lot, doesn't it? And what do we have? Well, we have that 1 needs to equal C1 plus C2 minus 5. And 1 needs to equal minus C2 plus 2. Well, this second equation is pretty quick to solve. We say, oh, C2 better be 1. All right, well, that was good. Now that we know C2, we can come up here and update this equation. We get 1 is equal to C1, and then we have a plus a 1 and a minus 5. Well, that makes minus 4. And that tells us what? Well, it tells us C1 better be 5. All right. Cool. Cool. Well, with that out of the way, what can we do? Well, we say, well, look, this C2 up here, that's going to become a 1. And this C1, that's going to become a 5. Because that's what we solved for. And so now we're basically done. We just need to write our final answer. And, okay, so I'm going to move this up a little bit. Not too far. And we get our final answer is x is 5e to the t, 1, 0, plus e to the minus t, 1 minus 1, plus negative 5, 2. That's a perfectly reasonable way to write it. Another perfectly reasonable way to write it is to say, well, we could also just put it into a single vector. So 5e to the t plus e to the minus t minus 5. And we also have 0 times 5e to the t, which goes away. And then a minus e to the minus t and a plus 2. And that's another way to do it. Both are fine. Both are going to give you the points, right? And that's what we want. All right, well, that was number 3. So, a bit of work there. Not too bad. 2 equations, 2 unknowns. We like that. Brings us to number 4. Use the eigenvalue method to obtain the general solution for the system of equations x prime equals ax, where a is minus 1, 2, 2, 2, and x is xy. All right. So eigenvalue method. Eigenvalue method says, hey, we're going to look at this matrix, and since we have a matrix, we're going to find the eigenvalues. So we start by taking the determinant a minus lambda I. All right, well, that's the determinant of minus 1 minus lambda, 2, 2, 2 minus lambda. And we would have a minus 1 minus lambda, a 2 minus lambda, subtract a 2 times a 2. All right, well, that would give us a lambda squared And then we have a plus a lambda minus 2 lambda. So plus lambda minus 2 lambda is a minus lambda. And then we have a minus 2 and a minus 4. Yes? Minus 2 minus 4 makes minus 6. Well, does it factor? Can we think of two things that multiply to minus 6 but would add to minus 1? I can think of two things. What about lambda minus 3, lambda plus 2? Let's check. Lambda squared? Good. 2 lambda minus 3 lambda minus lambda, and negative 3 times 2 is negative 6. Set this equal to 0, and we get two eigenvalues, 3 and negative 2. All right. Now, there's a way to quickly check to see if these are right. If you add these, you should get the same as if you added along the diagonal. Well, 3 minus 2 is 1, and minus 1 plus 2 is 1. If you multiply these, negative 6, that's the same as if you took the determinant. Minus 2 minus 4 is negative 6. So these are definitely the right eigenvalues. We have distinct real eigenvalues, which means that we are now going to go and find eigenvectors. So, just a side note here, we have eigenvalues. And now we're going to eigenvectors. Okay, good. Good, good, good. Well, how do we do that? For each eigenvalue, we're going to do the following. Just say, let's start with lambda equals 3. I'm going to look at a minus lambda I. So I'm plugging 3 into this. So minus 1 minus 3 is minus 4. 2, 2. 2 minus 3 is minus 1. I have to multiply that by something and get out 0, 0. So the thing is, your eigenvector is this something. So that's what we're looking for. Here's how I like to find it. I pick a row. That looks pretty easy. The second row looks a little bit simpler. And I say, all right, put that in reverse order. Negative 1, 2. And then change one of the two signs. All right, I'll change that minus to a plus. And that's the one I claim works. Well, you can check. Minus 4 plus 4 is 0. 2 minus 2 is 0. Okay, so we get our eigenvector eigenvalue pair. So lambda equals 3 is 1, 2. We do that again, right? Because we got two eigenvalues. So we repeat the process. So lambda equals minus 2. Okay, so we're putting minus 2 up into this expression. Minus 1 subtract a minus 2 would be a 3. It would be a 1. Right? Because it's minus 1 plus 2. 1. And then you have a 2. Then you have a 2. And then 2 minus minus 2 is 4. And we have to multiply that by something and get out 0, 0. All right. Well, again, pick a row. Here we go. That seems like a good row. And we'll write that in reverse order. 2, 1, flip a sign. I'll make that a minus. And now we check. Okay. 2 minus 2 is 0. 4 minus 4 is 0. And so that's our second eigenvector pair. Lambda equals minus 2. 2 minus 1. Now, we're almost done. We're after the general solution, right? That's what it told us, general solution. We found eigenvalues. We found eigenvectors. And at this point, you're probably thinking, well, great, this is a lot of algebra. When do we get the differential equation? Well, the algebra part is like the characteristic polynomial that we used to do. And now what we do is we say, well, we can translate these this information here into solutions. So this lambda equals 3 with the eigenvector 1, 2, you'd be e eigenvalue t, so e to the 3t, 1, 2. So that's a solution. Lambda equals minus 2, 2 minus 1, e eigenvalue t, so e to the minus 2t, eigenvector. So those individually are solutions. So how do we get all the solutions? That would be a super thing to do. Superposition. So once we have that, we say, okay, our general solution is some constant C1 plus some constant C2 times the individual solutions, and we're done. General solution, or what I might call general form. And huzzah, huzzah. A great huzzah went up throughout the land. So that's number 4. That leads us to number 5. Consider the homogeneous linear system x prime equals ax, where a is 2, 1, minus 1, 2. And again, parts A and B. Part A. Find the exponential matrix e to the at and simplify your answer to a single matrix. And then there's a part B. Using the exponential matrix, find the solution for the system given the initial values x of 0 equals 1, 0. Leave your answer as a single vector. So one vector to rule them all. All right, well, what to do? Before we find the exponential matrix, we always start problems involving a 2 by 2 matrix in the same way. So we're in part A. So first step is eigenvalues. Okay, so let's figure out what our eigenvalues are. So we're taking the determinant of A minus lambda I, and so that's the determinant 2 minus lambda, 1, minus 1, 2 minus lambda. And all right, so taking that, we have 2 minus lambda squared, and subtract our 1 times a negative 1. Notice that 2 minus lambda squared is the same as lambda minus 2 squared, and then you get a plus 1. Now, let's pause before we go any further. Remember that we're saying this equal to 0. Before we expand out, let's say, does it even help us to expand out? In this case, what do you notice? Well, this is something that's greater than or equal to 0. This is something that's 1. Can I add these two together and ever get 0? Well, no. And you're like, wait, what? Hold on, let me step back to my claim. Lambda minus 2 squared is greater than or equal to 0 if lambda is a real number. I think things are about to get a little bit complex. Yes. We're going to get some complex numbers here. Woohoo! Or dope, depending upon how you feel about complex numbers. And so to solve for lambda, we'll do a little bit of moving things around. So lambda minus 2 squared equals negative 1, which says I need to square something and get negative 1, which means, lambda minus 2 had to be either plus or minus I, or we get lambda equals 2 plus minus I. Okay, so these are our eigenvalues. Now, why did we find eigenvalues first? Because the type of eigenvalues you have will drive the way you find e to the at. And I'm going to grab the formula sheet and just talk about the formula sheet for just a minute. You'll notice in the formula sheet there's a very small, narrow portion which deals with items from this part of the course. Namely, these 3 formulas. And what do they all have in common? They all involve e to the at. So there's 3 of them. So let's just do a quick recap. There's the e to the at is the phi of t. Phi of t is fundamental matrix. Phi is 0 inverse. This is when we have distinct real eigenvalues. That's the one we pull out. Well, that's not our case. Then the next one we have says, oh, e to the at is e to the lambda t times I plus t a minus lambda I. This is the one we pull out if we have repeated eigenvalues. So like lambda lambda, we don't have that. And then there's the third one. E to the at is e to the alpha t cosine beta ti plus 1 over beta e to the alpha t sine beta t a minus alpha I. This is the formula for complex eigenvalues. Okay, so recap. Distinct real, repeated, complex. And this is your smorgasbord offering for how do you compute e to the at. So we are going to come and use this formula. Now, do we have to? No. We could do it a much longer and more painful way. Do we want to do that? No. No. We love ourselves. And because we love ourselves, we're not going to subject ourselves to a lot of computation needlessly. We're going to be careful and say, look, let's be smart. Let's use the tools they give us. All right, so this 2 plus minus I, the 2 is the alpha, and the beta is 1. So you can think of this as a 1 times I. Now, what do we have? I'm going to copy the formula. Sorry, my screen is a little bit small, but I promise you I am copying the formula down. We have that e to the at is e to the alpha t cosine beta t times the identity plus 1 over beta e to the alpha t sine beta t times a minus alpha I. Okay, so put this away. Maybe we'll use it again. Who knows? We still have another problem. So alpha is 2, beta is 1. So for us, this becomes e to the 2t cosine t times the identity, 1, 0, 0, 1. Beta is 1, so 1 over beta is 1. That's very convenient. So we have plus e to the 2t sine of t. And then we have this a minus alpha I. So here's a minus lambda. Alpha I is 2. So think of it like subtracting 2 off the diagonal. What would that be? Well, that would be a 0, 1, minus 1, 0. And in particular, it doesn't say that we have to put it together, but let's, simplify your answer to a single matrix. We do have to put it together. So our single matrix, well, you distribute in and then you add. So here you'd have e to the 2t cosine t and then plus 0. Then you'd have a 0 plus an e to the 2t sine of t. Then downstairs you'd have a 0 and a minus e to the 2t sine of t. And then you'd have a e to the 2t cosine of t plus a 0. And there we go. Huzzah! Huzzah! That's part A. All right, so we found e to the at as a single matrix. Now, part B. We're only halfway through this problem. It says, using the exponential matrix, okay, so we're going to use this matrix. Find the solution for the system given the initial values x of 0 is 1, 0. Leave your answer as a single vector. All right, now, how do we do this? Well, here's the fun fact. if you have x prime equals ax and x of 0, so that's your setup, then the solution looks like e to the at times x of 0. It's very similar to what we started with at the beginning of the semester. So we say, oh, well, hey, hold on a second. We have e to the at, and we have x of 0. It's 1, 0. So our answer, x, looks like e to the 2t cosine t minus e to the 2t sine of t. I'm just copying down e to the at, e to the 2t sine of t, e to the 2t cosine of t, times 1, 0. And so we multiply that out. And if we do that, well, we get x equals e to 2t cosine t plus 0. And then minus e to the 2t sine of t plus 0. And we're done. So if you understand how to use your exponential matrix, and you have your exponential matrix, then solving initial value problems is nice. All right, that's number 5, which means we just have one problem left. One last problem to enjoy. Number 6. Consider the homogeneous linear system x prime equals ax, where a is 3 minus 5, 0, 3. Part A, find the exponential matrix, e to the at, and simplify your answer to a single matrix. Part B, using the exponential matrix, find the solution for the system. Given the initial values, x of 0 is 2, negative 1. Leave your answer as a single vector. All right, so very similar to the last problem, just a different matrix. So what could be different? Well, let's find out. We start by finding eigenvalues. It always helps us because that's going to say which path do we take. So when we're doing our eigenvalues, we have our determinant of a minus lambda I, and that's the determinant 3 minus lambda, negative 5, 0, 3 minus lambda. Well, that's 3 minus lambda squared. Subtract 0. Or if you like, that's lambda minus 3 squared. Well, when is that true? It says, hey, we have repeated roots. Okay, good. Well, now we say, all right, what do? We head back to our formula sheet. Say now we grab the repeated roots first, right? Distinct real roots, repeated roots, complex roots. And we say, all right, that's our one. That's the one that we want. Okay, so we have our formula, and it is e to the at is equal to, and sorry, I put this away too quickly. All right, e to the at is e to the lambda t times the identity plus t times a minus lambda I. All right. So now what do? Well, we just put in what we have. So, lambda is 3, so we get e to the 3t times the identity 1, 0, 0, 1 plus t times a minus lambda I. So here's a minus lambda I in general. We just put in lambda equals 3, and that would be a 0, minus 5, and a 0, and a 0. Okay, so that's e to the 3t, and now we add these together. Well, you're going to get 1 plus 0, 0 minus 5t, 0 plus 0, and 1 plus 0. Now, that is a single matrix. The question is, do they want to insist that the e to the 3t goes in? You know, I don't know. I feel good about this answer, but, you know, we could also just distribute that e to the 3t in. So I'll do that. E to the 3t minus 5t e to the 3t, 0, and e to the 3t. All right. So there we go. That's part A. Now notice, once we had the eigenvalues, we're just like, oh, now we know what we're doing, and we get our answer. And so it's nice to have the tools to make things good. Okay, so as in the last problem, so I'm not going to rehash that, but it says, look, we have e to the at, we have our initial conditions, so our x is e to the at times our x0, which is e to the 3t minus 5t e to the 3t, 0, e to the 3t, and then times by 2 minus 1, which would be, well, we'd have 2 e to the 3t, minus 1 times minus 5 makes a plus 5t e to the 3t, 0, and minus e to the 3t. And that's the answer. And that's the end. Because this was our last problem. Where does the time go? It goes so quickly. And so, all right, I hope you had fun. And notice that once you understand the power of e to the at, we use it for initial conditions. You can also use it to get general form. Because you might say, well, how do you get general form? You do superposition of the columns. Because e to the at is a fundamental matrix. So if a problem asks for fundamental matrix, e to the at. Ask for general form, superposition of columns of e to the at. Ask for initial condition problem, e to the at times x0. It's just boom, 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 boom. Life is good. Life is wonderful. So it's a very powerful technique. All right, well, keep up your practice. You can do this. Don't be intimidated by matrices. They're not scary. They are powerful allies to help you solve problems. I know you can do this. I know you can be great. And I hope you do well on whatever you're getting ready for. Good luck. And I think we'll see each other one more time, right? All right. I hope so. Okay. Bye.